All right, hello, taking a look at chapter 3.4, the derivatives as rates of change, and really kind of what that means in terms of their applications. All right, so the derivative is really the slope of a tangent line, right? So that's great. And we kind of have talked about how this tangent line can provide an approximation of what a function is doing. All right, so based on the rate of change of a function, the derivative of that function, that in general, that tangent line should still be pretty close to the original function. All right, so if the function is supposed to be here, we can create a tangent line here. All right, so have a function, we can create its tangent line. If you go just a little bit away, the tangent line and the function should still be pretty close to each other. Right? And so by using that rate of change of our derivative, all right, we should be able to find an approximation of the original function. Okay, so what this basically does for us, we know we have this equation y minus y1 equals m times x minus x1. That is the point slope form of a line. If you move the y1 to the other side, this is exactly the equation of point slope form, slightly rearranged. Well, y1 is basically just like f of a, f of some x value. M is the slope of our tangent line at that point, so f prime of a. And then x minus x1, well, x1 is the a value, okay? And I have an approximation here. It's almost equal to the original function, okay? So your original function will be very close to this tangent line approximation. All right, let's just do one and kind of figure out what we're talking about here. Okay, so if we have f of x equals x squared, we have this quadratic. All right, and I want to know 3.1 squared. Okay, I want to plug 3.1 into this function. We could do that. It would not be incredibly difficult. We can plug 3.1 in. But the idea is that we could also do this and get a decent approximation using a tangent line, and it's pretty easy. All right, step one, all we have to do is know the derivative. That looked really terrible. All right, what is the derivative of f of x? Well, 2x, that's just a power rule. All right, that's great. So we have f prime of x equals 2x. Well, we have an x value of 3 that we're working with. So we can plug in 3, f prime of 3, 2 times 3 equals 6. All right, so the slope of x squared, the slope of that function, when x is 3, is about 6. We can use that equation to make a tangent line. All right, so that's our a. 9 is f of a. We know if we plug 3 into here, 3 squared is 9. All right, so we can say our tangent line in general would be y equals our y1, 9, plus our slope, 6, x minus 3. Distribute that. All right, so we have a tangent line y equals 6x minus 9. All right, the entire idea of linear approximation is that f of 3.1, plugging 3.1 into this equation is pretty much the same as doing 6 times 3.1 minus 9. All right, so big picture idea. I can do this literally in my head. 6 times 3.1, that's 18.6, take away 9, that's 9.6. That's really quick, that's really easy, and that's there. To do 3.1 squared, so 3.1 times 3.1, I'm going to go old school here. $9.61. Well, almost the same. Okay. General idea is that linear approximation will be usually pretty accurate. Graphically, what this is showing right, we have our x squared, we have our tangent line. The general idea is as long as you choose an x value that's relatively close, the tangent line and the function are going to line up really, really closely. Okay, so this is how we actually do. I know I've talked about this in the past in other videos, but this is one of the major purposes of derivatives, of finding these things, is to be able to do this linear approximation. It's very quick. It's very easy. For an x squared graph, it's not super useful. Just to evaluate an x squared graph is easy. But for a more difficult equation, a more difficult function, derivatives are easy, but plugging things in can sometimes be a little tough. All right, so let's try another one. All right, so f of x equals 3x cubed minus 4x plus 1. Plugging in 2 would be pretty easy overall. 2 cubed, that's 8. 8 times 3 is 24. Minus 4 times 2, so minus 8. So that's 16 plus 1, 17. All right, so that's like our A. That's like our f of A. Again, we could do that in our head. If you asked me to plug in 2.2, that's going to take me a long time to be able to cube 2.2, multiply it by 4, add all those things together. All right, but I can do the calculus part really easily. I can take its derivative. 3 times 3 is 9x squared minus 4. That's just power rules. Now I can plug in 2 to that. 2 squared, that's 4. 4 times 9 is 36. 36 minus 4 is 32. So y equals, make my tangent line, 17 plus 32 times x minus 2. Distribute here, I've got 32x minus 64 plus 17. That is what? 47. Okay. So linear approximation says, hey, to approximate f of 2.2, do 32 times 2.2 and then subtract 47. All right, so 32 times 2.2. Yeah, I guess that one's a little bit tough. Maybe I will pull out the calculator for that. I know, kind of pointless for what the entire purpose is. The point is to be able to do some of these approximations without having to use a calculator. I'm getting a little lazy in my late years, I guess I'll have to admit. So we got 23.4. Okay. Now, what would it be if we actually did just put in 2.2? 3 cosine minus 4 times 2.2 plus 1. All right, 24.144. All right, so a little bit off by about 0.7, so not quite as great as that last problem, but still in the right ballpark. Okay, and so that is just one of the ideas that we have with calculus. We want to be able to create a tangent line, use that tangent line to approximate a function. All right, and there we go. So one of the reasons why this one is a little bit more off than the last one, here we were from 3 to 3.1 is only 0.1. From 2 to 2.2 is off by 0.2. So that little extra distance away from our original x value does cause some issues. But it is what it is. There are some other methods that we will eventually get to that are better than just linear approximations. We'll get to these things called a Taylor series, and I believe you have one in your project that allows you to use multiple derivatives to kind of create a little bit larger of a function than just a linear. We can create a quadratic or a cubic or a quartic, or really as big of a polynomial as you want, just using some derivatives. And it does a really, really nice job of approximating. All right, so another application of derivatives as rates of change. So again, derivative kind of talking about the slope of a tangent line, how a function is changing at a certain value of x. And it's the idea of partial motion. So we started particle. I didn't spell. Particle motion. So when we start talking about calculus, applying it to the world, one of the biggest ideas is just how things move, and applying it in a physics mindset. So a function represents the position of an object. The first derivative represents its velocity, its speed. And its second derivative represents its acceleration, how the speed is changing. So the velocity, speed, is talking about how the position changes. Acceleration is talking about how the speed changes. Okay, so we have a ball dropped from a height of 64 feet. Its position t seconds after being released can be modeled by this equation. All right, so find the time when the ball hits the ground. Well, this is the position. So when the ball hits the ground, that's a height of 0. So I'm going to take my equation and I'm going to set my position equal to 0. And I'm going to solve. I would subtract the 64, divide by 16, and that is what? 3. Right? Or is that 4? That's 4. Take the square root. All right, and we get plus or minus 2. Well, this is the math physics issues. I hope we know that we can't have a negative time. So 2 seconds. It would take 2 seconds for this ball to hit the ground. All right, find the velocity of the ball when it hits the ground. Well, the velocity, v of t usually, is just the derivative. All right, so we find the derivative of our function. That's just a power rule, 2 times negative 16. And the derivative of 64 is 0. So we just have negative 32t. All right, and that in units would be feet per second. All right, our ball should fall right now 32 feet every second. Now we want to find the velocity when the ball hits the ground, and we know time is equal to 2, so we want v of 2 All right, so the ball is moving at negative 64 feet per second. Now let's just make sure that made sense. Negative 64, it is negative because that ball is dropping in height, right? The height of that ball is decreasing. So that is why that would be negative. All right, letter C, find the acceleration. Well, the acceleration is the derivative of velocity, which is the second derivative of your position. So the second derivative, we did our first derivative, so our second derivative is negative 32. That's just a power rule. All right, and it would be feet per second squared. Okay, so where these things are coming from right, so we had f of t and we did d dt. So f of t, that's like a y, a feet. So we took the derivative of feet per second, okay, and that was here. So our time was there. We then did the derivative with respect to t of our feet per second. And so that's where the second squared comes from. Okay, so feet per second squared. Notice there's no number to plug in, so our acceleration at t of 2 is still just negative 32. It doesn't matter what time we're choosing, the acceleration is negative 32 feet per second squared. Now, you'll notice that a lot of times that acceleration is going to be negative 32. Negative 32 feet per second squared is actually the pull of gravity here on Earth at sea level. Negative 32 feet per second squared. So this problem is assuming no air resistance, nothing crazy, no wind issues. So there we go. All right, a particle moving left and right along a straight line. Its position at time t in seconds is given by this function. So we have a position, and t has to be greater than 0. Find v of t, the velocity. Well, v of t is just the derivative of position. So we find the derivative. The derivative of this polynomial, we just do each term. It's nothing, no big product rule or quotient rule, nothing crazy. We just have to do our derivative. So derivative of t cubed is 3t squared minus 18t plus 24. All right, when t is equal to 1, is the particle moving left or right? Well, let's plug in 1 into our derivative. V of 1, if we put 1 in here, it would be what? 3 minus 18 plus 24. 3 minus 18 plus 24 is 9. Well, it's positive 9, so that means it is moving right. At a time of 3, our velocity, is it moving? All right, so our velocity, how it's moving, plugging in 3. 3 squared, that's 9. 9 times 3 is 27. 3 times 18 is 54. So what? 51 minus 54, negative 3. So that means it is moving left. It's negative. Negative velocity. In this case, it's moving left or right. So 3 to the left every second. And when t is 5, this is going to be a little harder in my head. 3 times 5 squared, so that's 125 minus 90 plus 24. So we got what? 35 plus 24 is 59. So it's moving right at a rate of 59 units per second, feet per second. It doesn't say what units that position's in, so 39 units per second to the right. All right, at what time does v of t equal 0? This would mean the particle is at rest. So we would take our derivative and we would set it equal to 0. All right, to solve this, the first thing I noticed that 3 goes into everything. I can then factor that. So at 4 and 2, our position 0. Over what periods, intervals, is the particle moving left versus when is it moving right? Well, to that, we set up what is called a sign chart. All right, so we start with t equals 0. So we don't need to worry about negatives with this. It says t is only bigger than 0. We then put our numbers on our number line. We know the particle is at rest here, and it's at rest here at 2, and it's at rest at 4. And those are the only possible times it could be at rest. That's the only times our derivative is equal to 0. Okay, so we know it's going to be moving for every other moment in time. All right, so to create a sign chart, what we do is we pick a number in each zone. Like when time is equal to 1, okay, in between 0 and 2, when time is equal to 1, how is our function, how is our speed, how is it moving? Well, what's our velocity when t was 1? Well, hey, we did that. When t was 1, our velocity was 9. So we know between 0 and 2, that velocity is positive. So we are moving to the right. From 2 to 4, for instance, when t is 3, so a number in between those two, our velocity was negative. So it's going to be moving left from 2 to 4 seconds. And then after 4, so that when t was 5, it was 59. So it will be moving right. So what intervals was it moving to the left? For our t values in the set of 2 to 4 seconds. Do you remember interval notation? I don't know if this notation made sense. It's a little tough with my t values. All right, if you see this kind of almost looks like a backwards E, that means in the set of the following numbers. So in the set of 2 to 4, that particle would be moving left. Our derivative, our velocity is negative. So we are moving. Derivative means we're moving. All right, and it being negative means we're moving left. So when is the particle moving right? Well, that is for t values in the set of 0 to 2 and union 4 to infinity. All right. So 2 sets there from 0 to 2. Remember it said start at 0. I guess we didn't put a bracket on that. Right. We had time equal to 0. To infinity, we didn't have a limit on how big t could be. All right. So now we're given a graph instead of a function. So we have a position function and how it's moving along in a straight line. So use the graph to determine the intervals where the velocity is positive, negative, or 0. All right, so basically in my mind, that means make a sign chart. All right, so we start at 0. This thing stops at about 7. So we want positive, negative, or 0. Okay. So what I'm seeing is that when we start at 0, the graph is going up. That means our function is increasing until about this spot right here. So at about 1.5. So from 0 to 1.5, we are increasing. All right. We are then doing nothing. We're not increasing. We're not decreasing. We're just at that 0 height. We then decrease until here at 2. From 2 to about 5, we have just a flat graph. Our position is not changing. We're not increasing. We're not decreasing. From 5 to 6, our function's decreasing. And from 6 to 7, our function's increasing. Okay, so this is called a sign chart. So we are increasing. So our velocity is positive. So we're increasing from 0 to 1.5 and from 6 to 7. we're decreasing from 1.5 to 2 and 5 to 6 and 0 from 2 to 5. All right, sketch the graph of our velocity function. Whew, that's a little bit tough. We'll have to make a new piece of graph paper for that. All right, so 0 to 1.5, we are increasing. And we start out increasing really fast, and then we slow down. So it would start out here. We're increasing, so we're above 0 until what, 1.5. Notice we were increasing really fast for a while, and we slow down right near the end. All right, from 6 to 7, we are also increasing. So we were 0 at 6, and we are increasing slowly and then increasing quickly. So probably something like that. Let's see, we're decreasing from 1.5 to 2. And at 2, we're back to 0. So we don't get a very big decrease. We're constant, a 0 slope from 2 to 5. And from 5 to 6, we were negative. But we go way lower, so that speed gets quickly down. So we would have a velocity graph, something like this. All right, to determine the intervals of time where this object is speeding up or slowing down. Okay, so that means our acceleration. Are we speeding up or slowing down? Okay, so we want to look at our velocity function, and we want to figure out when is the graph of velocity changing. So we know v of t is not changing. Its velocity, the acceleration, the derivative of velocity, is 0 at, let's see, somewhere in between 1.5 and 2. It's 0 from 2 to 5. And then it would be 0 again at about 5.5. All right, our velocity is negative. We are decreasing. Our acceleration is negative. We are decreasing from 0 to 1.75. We are increasing our velocity from 1.75 to 2. We're 0 here. From 5 to 6, this velocity function, so our acceleration, is decreasing. It's going down. From 5.5 to 6, we are then increasing again. And actually, we increase that entire last bit of time. So from 5.5 to infinity. So our acceleration is positive from 1.75 to 2, and from 5.5 to infinity. Our acceleration would be negative from 0 to 1.75, so we're slowing down. And then from 5 to 5.5. All right, so trying to apply these ideas, what a derivative means in terms of position to speed, and then the derivative of speed is acceleration. All right, so I love the idea of saying, and I said this in the last video, the velocity is how your speed is changing. Okay, so if I'm in my car, just where my car is, that's my position. That's easy enough. All right, is my foot on the gas pedal? Okay, If my foot is touching the gas pedal, that likely means we're moving, okay? If we're moving backwards, my velocity would be negative. If we're moving forwards, our velocity is positive. Great. All right. Velocity in general, pretty easy to understand. Acceleration means my foot's on that gas pedal, so my car's moving. Great. Acceleration means, am I pushing down on that gas pedal? All right. To make my car speed up. So not just am I moving, but is my car increasing in speed? All right. Am I watching that speedometer increase? Or am I taking my foot off that gas pedal a little bit? Am I letting the speed decrease? Am I slowing down? Me slowing down means my acceleration is negative. Okay, so I can still have a positive speed. I can still be moving forward, but my acceleration can be negative because I'm slowing down. I am still going forward, all right, but a negative acceleration just means my foot's coming off that gas pedal, okay, and my car is slowing down. All right, cool. So hopefully we have a decent understanding. At this point, after 3.4, we should be prepared to work on that first project. All right, so take a pause to going through videos. Let's take a look at that first project. And we should then take our first test, and we will go from there. All right.